Hello friends, I cordially welcome to my channel Chemigeek, where we are going to dynamize our knowledge through problem solving. Today we have this topic, predicting the possible mechanistic pathway of organic reactions, on which we are going to solve one problem. As you can see, there are two molecules. One is this 2,5-hydroxy tetrahydrofuran 3-yle ethanoic acid, which is on the left hand side, and the other one is the 2,5-oxo tetrahydrofuran 3-yle ethanal. So as you can see, on the left hand side, the main chain has 2 carbons, which is the ethanoic acid part, and on the right side you have the main chain with 2 carbons, which has the aldehyde part. So it is the ethanal part. On the right hand side molecule, you can also see the tetrahydrofuran and the ketone group, whereas on the left hand side you can see the tetrahydrofuran and the hydroxyl group. So this is 5-hydroxy because it is in the 5th position of the tetrahydrofuran ring. So let us go step by step now. If we divide this entire problem in 4 different steps, we have the first step, correctly numbering the atoms present in the molecule. Second step is identifying the organic functionalities or groups, we can call them, present in the molecules. The third step should be understanding the possibilities available to the reaction on the basis of the substrate and the reagent. So we have the substrate, which is on the left hand side, the molecule on the left hand side, and the reagent is nothing but aqueous acid. So the fourth step should be solving the problem on the basis of the possibility that explains the formation of the given product. So we have a certain product on the right hand side and a certain substrate on the left hand side. So according to the product, we should think about the mechanism, because the question is, explain the following observation mechanistically. So we have divided the whole solution in 4 different steps. So let us focus on the first step, that is correctly numbering the atoms present in the molecules. Looking at the ethanoic acid portion of the substrate, we can number the carboxylic acid carbon as number 1 carbon and the other carbon as number 2 carbon, and the second carbon of the main chain, that is ethanoic acid chain, is linked with the tetrahydrofuran moiety. And we can see that if we start numbering from the oxygen atom, then second, third, fourth and fifth, then the third carbon of the tetrahydrofuran ring is attached to the second carbon of the ethanoic acid. Similarly, on the right hand side, the first carbon is the ethanal carbon, the second carbon is the carbon next to the ethanal carbon, that is the alpha carbon, and then we number the tetrahydrofuran ring considering the first atom as the oxygen atom, the second the next carbon, the third as the next carbon which is attached to the second carbon of the main chain, fourth and fifth carbon has the oxo group, that is the ketone group. Now we are moving on to the second step of our solution, identifying the functionalities groups present in the molecule. So we can see first we have the carboxylic group, secondly we have the hydroxy group, and in this portion we also see a hemiacetal group. As you can see, this fifth carbon is nothing but the central carbon of the hemiacetal, because when we think about hemiacetal, it is the carbon which is linked with four different groups. One is hydrogen, the second is the hydroxy group, then the third is the alkoxy group, and the fourth is the alkyl group. So the alkoxy group that is shown, this can be seen on the molecule that we have on the left hand side of the tetrahydrofuran ring. The hydroxy group is this one, and the alkyl group is the fifth carbon of the tetrahydrofuran ring. So this is the hemiacetal group which we have. Why I have shown this hemiacetal group here? Because we will eventually see that for the conversion of the reactant to the product, or let's say the substrate to the product, we will see that this hemiacetal will transform into aldehyde. Now we are moving on to the next step, that is step number 3, understanding the possibilities available to the reaction on the basis of the substrate and the reagents. So we have three pathways. The first pathway is the protonation. Since the reagent is nothing but aqueous acid, it can protonate the carboxylic oxygens. So if we consider this option, it can get protonated, but if it gets protonated, it will make the carboxylic carbon electrophilic center. It can form a cyclic ring like this. So if you can see here, the carboxylic oxygen gets transformed into the hydroxyl group along with the original hydroxyl group of the carboxylic oxygen on the carboxylic carbon, and the oxygen which was originally in the hydroxyl group becomes a ring oxygen, which is a 6-membered ring. But in this case, we do not see that the mechanism is moving towards our desired product. So we can easily evade this option. Next, it can also protonate the hydroxylic group which is present on the 5th position of the tetrahydrofuran ring. If it protonates this hydroxylic group, the oxygen of the tetrahydrofuran ring can push its electron so as to stabilize the oxygen and knock out the hydroxyl group as water, forming an oxonium ion as shown here, but this will not again lead to the desired product. So clearly it shows that this has no option to the desired product. Also, protonating the carboxylic oxygen is also not going to give us the desired product. So we are left with one option, that is protonating the tetrahydrofuran oxygen. These are just the option. I'm not talking about whether it will form a stable product or not. Whether it will lead to our desired product or not is the question, because the question has already been given and we are asked to give its mechanism, right? But if we protonate this furan ring oxygen, it will clearly lead us to a possibility of ring opening. And after it opens the ring, it can form, this oxygen will form a hydroxyl group, which can once again interact with the carboxylic carbon and possibly form a lactone ring, and can possibly form a lactone ring. So this is one pathway which can absolutely produce our desired product. So step number 4 should be solving the problem on the basis of the possibility that explains the formation of the desired product or the given product, right? So we will be protonating the furan rings oxygen first, as shown previously. Once this tetrahydrofuran rings oxygen is protonated, the hydroxyl group on the 5th position can push its electron from the oxygen atom towards the carbon which is attached to the tetrahydrofuran rings oxygen, which is protonated, and can stabilize this by opening the ring. So this is the starting material, or we can also call it the substrate. This, on treatment with aqueous acid, is producing a molecule, or let's say an intermediate, which has an open ring structure. Now it can also get deprotonated because there are plenty of water. The water's oxygen can take away the proton, and again it can reprotonate the carboxylic acid's carbonyl oxygen. I am referring to the carboxylic acid's oxygen as carbonyl oxygen and the hydroxyl oxygen of the carboxylic acid, considering that carboxylic acid is a combination of a carbonyl group and the hydroxyl group together. So once this carbonyl oxygen of the carboxylic group is protonated, it can go like we have the mechanism of Fischer esterification for lactonization, right? So it will form a lactone ring, a 5-membered ring, 5-membered lactone, and the hydroxyl oxygen can push its electron on the electrophilic carbon. This is also an electrophilic carbon because it is attached to an oxygen which is having a positive charge, and therefore it will pull the electrons and it will form a lactone ring, a 5-membered lactone ring like this.
But before this lactone ring is formed, this geminal dihydroxy group needs to be converted into a carbonyl group, eliminating a water molecule like this.
Alright, so first it will deprotonate and it will reprotonate a hydroxyl group. Let's say this is a proton transfer basically. So once this hydroxyl group is protonated, it can eliminate one more water molecule, and the hydroxyl group can stabilize by formation of a carbonyl bond. because CO is the most stable bond in organic chemistry, so it can form a ketone like this. And this you can clearly see I have just reversed, or let's say I have just taken the mirror image. So this is exactly the product, the desired product, right? So thank you very much for watching this video on Chemigeek, where we are going to dynamize our knowledge through problem solving. We are going to bring many more videos like this on problem solving in chemistry. Please like, subscribe and share our channel with your friends and all the chemistry learners you know. Thank you.